Good afternoon, the panel judges and the audience. My name is Kesh Keshavan. I am the VP for Business Development for Blacksand. And Wyatt McNeil is a PhD student at University of Utah. He will be doing most of the talking. I'm going to do a little bit of introduction about Blacksand and also the technology we're going to present today here. If you are familiar with titanium, you know that it's a light metal, but also it's got a high strength. And if you look at the ratio of the strength to density, which is called this specific strength, it's very high. If you are able to use titanium to replace steel, there will be significant opportunities. One of the reasons it's not being done today is because of its cost. Titanium is about 20 times or more higher than steel. So what we are going to present today is a technology that will show how we are able to produce a lower cost titanium, and also how the process that we are going to present enable you to produce a lower cost product. And my vision is that hopefully in next few years we will replace a significant number of products that you are currently using steel and nickel-based alloys with titanium. So if you look at the AUSA M77 cannon, today it uses 50% of it titanium. That's a significant weight reduction. You know, if you are able to reduce the weight, it's easy to carry, and also you'll improve the mobility. One of the key, as I mentioned earlier, the obstacle for use of titanium, especially in military, aerospace, and Navy, is that justification of the cost increase. And so Dr. Zach Fong, who is a professor at University of Utah, has been working on the titanium metallurgy for the last 4 years. Actually, this work is a result of the initial work he was doing on metal hydrides for batteries. And he's also a leading expert in tungsten carbide hard materials synthesis. He was able to use his background in tungsten carbide technology as well as hydrides, and the result was the development of titanium powders at a lower cost. So we will go through and explain how that was done. Blacksand is a startup company. They own exclusive license to all the patents related to the titanium metallurgy. They're located in Salt Lake City, and they have at least 3 major patents, and most of them are exclusively owned. Since my presentation in Washington at the xTechSearch, when we were competing for the top 10 position, at that time we didn't have any partners to work with. Since last October, we have 2 major affiliations that we are working with. One of the companies have got the exclusive rights for use of this powder for additive manufacturing. Because one of the technology we are not covering here is how to make a spherical titanium alloy powder at significantly lower cost. So that is, we have licensed to a company exclusively, and they're actually a major supplier for military and aerospace and others, superalloys manufacturing company. The other company we are working with is essentially in the beginning stages for this technology that Wyatt is going to present, and that's Boeing. They have been our partner for a long time during the DOE project, and they are very eager to demonstrate certain commercial parts for this year as well as going forward next year. So Wyatt is going to briefly cover the technology, and then he's got a bunch of parts and others. He's going to demonstrate what Blacksand Technology is about and how it will make an impact to military applications.
Perfect. So just by a show of hands, how many of you guys know what powder metallurgy is specifically? Okay, so a few of you. So basically what we do is we take metal powder and we consolidate it into a solid material, okay? So you can do that by having a fine enough powder, and you basically put it in an oven, kind of like a cake. I didn't know about this a year ago, just to give you guys an idea. So I was fresh at the time, right? Just like an oven, just like a cake, you put it in the oven, and then that will consolidate into a solid part, right? So that's the basis of our concept here. We basically take metal powders, and we can make a solid part that has, well, our part specifically, equal strength to what a forged material would have. So rather than having to go through the whole melt process, the whole forged process, the whole high temperature, high consumption, high energy process, we can use lower energy, lower cost to produce similar products right there. So I've got a video I'm going to show, and then I'll kind of walk you guys through this as we go along with it, just to kind of show you how our process is, what it does, and how it produces stuff. Good. Does it not have any sound? No worries, I can talk through it until we get that going. So this is a traditional connecting rod for a vehicle where it would have to be made extra large to be by forging, right? So you have an oversized process. Hold on, let's see what they're doing. No worries, we'll just go with this. Just can you back it up like 15, 20 seconds? Perfect, we'll just go with that. So here we have a preform of a connecting rod. It has to be made by multiple forging steps. So first it's cast and then it's forged out to this shape, right? So this is to get this mill product, it's extremely energy expensive, or intensive and expensive to do this. And you have an oversized part. So this is just a rough preform that's going to have to be subjected to basically massive amounts of machining, as many as 18 steps of machining. So you can see through this animation, you have approximately 80% of the material that you would have goes to waste product to scrap product. So we start with 5 kilograms, for example, we would go to 1 kilogram of parts. This is a diagram showing the inside of the material. It's what we call microstructures, just showing how fine the material is in there. So it's on the order of several microns, basically, on the very bottom, or as close as you can get. So this is a conventional powder metallurgy process that I was talking about, where you make it essentially closer to the same shape of the material that you want. And I'll go over how we do this, but generally, that's the shape that you would get. So it's a lot closer to the original shape. This eliminates a lot of the machining steps that you would have to do. So here we put it in an oven and vacuum sinter it. Put it under high vacuum, because titanium reacts with oxygen, and you have an inert gas in there that allows you to heat it up and you get a fully dense material. You have to machine a lot less, so you have 9% scrap compared to 80% scrap, and you can go from 1.1 kilograms of parts to 1 kilogram of final parts, for example. The issue with this standard process is you get extremely large grains. So you remember on that first picture how fine they were. On this one, they're comparatively massive. Now, for me and you, they're still very small, but on a microstructure scale, they're very large difference in size. So with our process here, we have a similar near-net shape manufacturing process. So we can get that same advantage of having material that's the same shape and the same size. We sinter it, as you can see here, and then we introduce hydrogen gas while sintering it. Now this is what we basically call a beta stabilizer. It's a temporary alloying element is what hydrogen is, but it stabilizes the materials in there and it allows you to make finer grains on that. So we get the advantage of having a near-net shaped part while also having the advantage of stronger materials due to the fine grains. And I'll explain all that in a minute also. So we still have the advantage of having machined parts, we have less scrap, and we have less machining steps. So here's our material where it's still that very fine material, and I'll have an image of that later that has all of them side by side. But you can see that ours is a lot smaller than vacuum sintering standard. This is a fatigue test. So basically when a material undergoes a cycle, that's a certain amount of force that it undergoes. This is an example of showing the conventional powder metallurgy on the left compared to ours in the middle, forged on the right. As you can see, conventional powder metallurgy has fairly weak fatigue properties, and that's just due to pores, large grains, stuff like that. You can see our materials are very competitive with forged materials, so they undergo fatigue properties or fatigue mechanical testing a lot further. You can see that picture on the bottom just showing the general sizes. There's a massive discrepancy as far as how that would go. So as you can see, ours, it allows you the benefit, it finds kind of a sweet spot of the advantage of near-net shaped parts while also keeping high strength, which was previously not being able to be done. So you get less material wasted, but you can have a higher strength. And then we're going to go over to my slides, if that's okay. Are there any questions at this point? Yes, sir.
What about laser sintering?
So laser sintering is not specifically what we're going into right here. Yes.
So if you look at the novelty in this process is the use of hydrogen for sintering. If you sit and ask why hydrogen, nobody would have thought about because for the last 50 years, all the titanium alloys are heat treated in vacuum furnace. So the patent is really the use of hydrogen during the sintering process. And so if you have to do with a laser, then you have to make sure that you have enough residence time. So we haven't really looked at any other thing, and also handling hydrogen in presence of laser is not very safe. So most of the furnaces that we are using has to be a hydrogen-rich surface to be able to get what we are looking for today.
We'll also go over that in a little bit within a couple slides. So basically, why does this matter? So like what your question said about let's do laser sintering, or let's say we want to do other stuff. So basically, previous to this, the most common practice was to do vacuum sintering. So let's say we wanted to make an automobile part. We would make the preform, which I'll discuss how we make, and then we would vacuum sinter it. And it has to be under an inert gas, either an inert gas or high vacuum, to keep oxygen away from titanium because it's so reactive. So if titanium gets in contact with oxygen, it'll immediately become titanium oxide, essentially, and it'll start to form layers, and it just becomes not a good material, basically. So we want to keep it titanium, not titanium oxide. So it has to be sintered under either high vacuum or argon. But previously, the issue with this was it has poor mechanical properties. The advantage of it is that it has near net shape to the parts, it's closer to the end shape, and so you get savings due to that. So we wanted to find a way to combine the advantages of powder metallurgy and still have that wrought or forged mechanical properties here. So ideally, the goal would be to replace steel with something that's as strong as itself, but it's lighter weight. It goes back to the saying of pounds become ounces and stuff like that. Our goal would be to replace parts that need to be replaced with high-strength materials, but that could save, the everyday soldier or whatever ounces or pounds and stuff like that. And I'll go over a couple of those examples up here. This is going to be a lot more hands-on demonstration, so the slides will be kind of shorter, but we'll go over that stuff, in person. So our technology relies on having a feedstock for the powder. So we need to have a powder production method that will allow us to produce parts, obviously. So one of the technologies we go over that we produce is what's called HAMR, and it's hydrogen-assisted magnesium reduction. And basically what that does is it takes titanium oxide and it reduces it with magnesium and hydrogen to give you pure titanium in the end. Previously, the most common process, I'm sure you guys have heard of the Kroll process, that uses TiCl4 or TiCl4, and it's a very harmful substance that can be corrosive and stuff like that, where we eliminated that and we started with titanium oxide, which is a very safe, we consume it in toothpaste. I mean, it's everywhere around us. It's very safe, it's very economically feasible and stuff like that. It creates titanium hydride, which is basically just hydrogen with the titanium to stop the oxidation. So to keep oxygen levels low, we use titanium hydride. This can result in about a 30% cost savings on raw material. So that's just our baseline for raw material. Now, when we get into preforms, that's how we create these parts, right? Now, there's a few different methods, but generally all of them go to that they have to be pressed into the shape of a part that's oversized. Because during sintering, you shrink, essentially. You're going to shrink a certain amount, let's say 15%. So you need to make a part that's 15% larger in all dimensions than that, and then it'll eventually shrink to approximately that same size, and then you can machine down from that. So you can either isostatically press it under high vacuum pressure with fluids, or you can also die press it. So die pressing, obviously the cost of the die would just cost more money, but I have methods for both right here in front of me. So that's the essential idea of that. Are there any questions on preforms? Okay. So this is our process. It's hydrogen sintering phase transformation. Basically, that's a very complicated way to say that we use hydrogen to sinter rather than it being under high vacuum here. So you can see on the left as we go left to right, we have that initial stage where we take it up to 1200 degrees C. whatever our part is, and then under a controlled hydrogen atmosphere, we lower it to 650 C, and then we sinter our part. After that, we dehydrate it, so we get pure titanium 6-4, Ti-6-4 alloy, 6 aluminum, 4 vanadium. So now we have, at this, I'll point at this because the laser's not want to work. At this point, we have a pure titanium 6 aluminum 4 alloy here, which is your high strength alloy. I guess I could just use this laser pointer at this point. Now, another advantage that we offer is that our material is easily heat treatable. So typically with forged materials, if you just take a standard alloy of whatever, it's not necessarily as strong as it could be because it needs to be forged to get stronger. The advantage we have is we start off with such a fine grain that we can easily heat treat it to give you different microstructures where we don't have to forge the material to get that, if that kind of makes sense. So that's another economic savings that we don't have to go through, energy consumption to hit the product itself or to heat it up.
So how much grain mobility do you have during that heating step?
During which heating step, pardon?
I mean, when you're at your dehydrogenization step,
yes.
How much of the grain size changes, and is there any mobility of the grain in that step?
Yeah, so I'll show you on the next slide. So you can see here that the left is the vacuum-centered microstructure. This would be similar to what we would have at this point right here. So directly after, let's say, this point, if we directly stopped it, this would be a vacuum-centered microstructure. If we just completely stopped and we didn't do anything with it, by using that temperature, we control the grain size to go a lot smaller, essentially. And not to get too complex, but what happens is the material, instead of precipitating elements along the edges of the grains, it precipitates the elements inside the grains. And that allows you to basically get a finer microstructure. And we can control it at this point, but essentially, for our cases, the smaller the better. So you can see here on the left, you have a vacuum-centered microstructure, and on the right, you have our base one. This is just kind of to give you an idea of how fine it is. Now, the reason we want fine microstructures is every grain you see acts like an energy barrier, right? So if you put a certain amount of force on the material, every time a crack appears, it has to hit the next grain, and that takes a certain amount of energy, okay? So the more grains you have in between that crack going, the more energy it's going to take, the stronger the material becomes, right? That's a generalization, but yeah. So here we have a tensile test. This is our, there's basically two properties that we care about as metallurgists or anyone really, and that's tensile and fatigue. Tensile is how much the material can undergo a certain amount of pressure before failing, and fatigue is how many cycles that material can undergo before failing, right? So here on the left, you can see in that shaded region, we have the minimums that ASTM requires. So they require all titanium 6-4 to undergo this same thing. And as you can see in the yellow and blue, that's what vacuum center basically shows, is you have slightly above minimums, but not really that much better. As you can see with ours, they not only exceed the ASTM standards, but they also exceed vacuum centering by quite a bit. And especially they see an increase past what's called the strain. So how much the material can, basically how ductile the material is. So we not only have stronger but more ductile materials than previously were invented. So if you think about it like this, we can have a material that's cheaper to produce but also stronger than what was previously able to be produced. And as you can see here, this is fatigue. So this is how many cycles it goes to. So this line right here, that is this 10 to the 7th, is basically what our cutoff is. They have a rule that, not a rule, but a generalization that if a material can undergo 10 million cycles, or 10 to the 7th cycles, it's considered to go on infinite. It can undergo that stress for an infinite amount of time. So anything past this line is generally extremely good, and it's going to last you a lifetime of, a service of whatever your parts may be. So as you can see, this is a typical curve. This green line right here is a typical area for what previously we were able to produce with vacuum sintering, whereas the red line and the blue line are what would need to be forged or all that stuff. So you can see here, these are actual data points of vacuum-centered products, where this line is, pretty much following directly in line with what we would see. And as you can see from ours are the yellow and the purple, we basically exceed not only vacuum-centered, but also forged material processes as far as for how much our fatigue is going to go in that lifetime. So basically, better material life of that. Here's a table just showing general what these things go through. So these specific numbers don't matter. The whole point of this is to show that our material outdoes ASTM standards and vacuum-centered standards by quite a bit. And as you can see here, it exceeds it by about 20, 30%, and then it's 10 to the 7th, or how many cycles it can go to at a certain strength is vastly stronger than others. As far as cost analysis goes, we have a lower production powder cost, as I already went over, by about approximately 30%. And then due to us having a higher near-net shape, we can reduce our machining costs by about 80% of material savings, of wasted material. So a lower energy cost, and it's environmentally safe due to not having that Tickle 4 chloride or corrosive materials. So there's that. I do have some parts up here I'd like to show you guys if you want to come up and look at them. I don't know if that's allowed. I hope it is. I don't know how the video camera is going to do this. I'm sorry. There's not really a way I can get around this. So as you can see here, this is a powder preform. This is just our standard powder that we would get, that we would produce. So it just turns out like that. And then this is a standard process for how we would produce a part, right? This is just an example. This isn't for sure what you have to do, but because there's many different methods with a die press or whatever. But I couldn't bring a 30-ton die press in here, so this is the best that I could do. So basically, picture that we could 3D print a part shaped like this. It doesn't matter. Just use your imagination for whatever part you would want. This is a connecting rod, for example. And then what we would do is we'd put a bag of some sort inside this, right? Close the part, just like so. And then you would attach this onto here and fill this part full of powder, right? So now the inside, if you can picture this, is full of powder, right? You expand it with vacuum so it fills the outside inside this chamber, or whatever chamber you'd want to do. And then now you have a part that is full of powder in this shape, right? This part is then placed into what we call a cold isostatic press, where it just surrounds fluid around the part, and then it presses that fluid at high pressure rates, right? And then that creates a part that is now surrounded by a bag, tied off, and then another bag to ensure that it's not going to get wet or whatever, and then it's relatively strong. Now, granted, this part had to fly here, so it cracked in 2 spots, but you can feel that strength of, like this spot, for example, or the other spots where it didn't crack at its weak point. So it's a relatively strong material, but it's not, fully dense or whatever. And then after sintering, this is a hip joint, for example. So we can create the powder preform that's similar to this shape, right? So this is after sintering. You can feel it. It's just as strong as whatever. We can reduce then the machining costs to something like this by 12 steps or 80% in some cases. So you can see that the advantage of that, and you can pass them around or whatever. So that's a general idea, right? Another option would be where you could 3D print molds like this, and then you could just apply them together, fill the powder up. Obviously, you'd have to seal off the sides, but then you could press it together and create a part like that. So that's for an example. As far as the connecting rod goes, obviously I don't want to say obviously, but we cannot make something this large on our scale. So our scale's significantly smaller than what this would be, where we would need a press that's either larger or a SIP that's larger. But you could do a part like this, exactly like this, just larger scale. It would scale up just fine. So now these two specifically are just to show you the weight difference of titanium, and we'll just pass them around. If you want to put one in each hand, these are not produced by me, they're produced by another company, but they're the exact same part specifically for a gun that I think would be applicable, just to show you a weight difference and to show you the machining difference right here. And then these are the initial raw materials that would be used for this. So that's a raw bar that would have to be produced, and then that's the amount of machine chips that would come from just producing one of those. So that's just kind of an idea to show you one particular part that could be used on a gun or whatever that we would want to go to, whatever we would see for that, and then how much material would obviously get wasted or have to get recycled and all that stuff. Now, every time this material gets recycled, it has to get reproduced, deoxidized, all that stuff. So as you can see, it would kind of go on from there. With specifics parts that we were looking at for the M240, the carry handle is one of them. Now, the M240, when it was redone, was made into a light version that had a lot more titanium on there. But when you look at a part like this, if you can have this kind of an example here, if it's produced by a bar that's 8 times the size or whatever, it has to get machined down quite a bit, whereas we could make a part that's similar to that shape and then lightly machine it down, just like I showed with the hip and the other parts. And then there's some more parts that I think would be applicable, but that's generally what we wanted to look at. So Are there any questions? Yeah.
So as far as the machining down,
Correct.
how much skilled labor is required for that, or is that automated?
Generally, right now, it's all automated. CNC presses are just programmed to whatever they want to do, and then they're just brought down. But when you consider that, when you look at materials, specifically materials costs on that, I've talked to a couple people that run machine shops and actually do work with military and aerospace. Raw savings matters more on large scale. So obviously, if you have, let's say, 10,000 parts, raw savings is going to be an extreme difference. But until you reach that threshold, the costs are going to be similar for raw materials. Now, machining steps, that's a completely different story, because the less machining steps they have to do, the less time their materials or their machines doing that to produce that material. Any further questions?
Early on you said 20 times was a rough.
So if you look at the steel today, it's about $2 a pound. Take it. So today steel is about $2 a pound roughly. And if you look at titanium, it's $40. And nickel-based alloys somewhere between $12 to $15, $20. So that's about 20 times. But sometimes if you want to buy the powder like what we use in powder metallurgy, it can go up to $100 a pound. So that's really the biggest barrier is if you can make the titanium powder at $20 a pound, you have a significant opportunities for use, especially replacing nickel-based alloys. And also you remember, because the strength is higher, you can use less material. So it's really taking advantage of the strength as well as the density. This one weighs about half that of steel, okay?
Yeah.
And the cost difference between.
So raw material cost or product cost?
Although it's probably not really a good indicator of what they're charging.
So it depends on part to part, okay? I think the parts that are material intensive and very limited in machining, the cost difference is not going to be the same. So I would say it's about 30% cheaper.
Yeah.
But if you include the machining costs where you scrap 80%, it could be an order of magnitude difference.
Yeah.
So one of the challenges we are going through in last 6 months is getting the right parts in terms of working with the customers like Boeing and other military applications. We had to be very selective for our proof of concept, and we have a couple of parts that Boeing is looking at. So if I say that it's going to be generally anywhere from 30 up to 100% cheaper depending on materials, scrap, as well as how much time it takes to machine it.
It's difficult for us to contact FN and be like, hey, we want to build your parts out of titanium.
So
really
since
super cool with
the
that.
last presentation I was here, so we have been working with a couple of scientists in College Station,
Yeah.
as a part of University of Texas Army lab there. And they have a couple of parts that we want to work with, but they have a current vendor, so we had to sign the NDAs with both the Army as well as the vendors. So that's one of the avenue we are going through. And they are pretty excited about testing these parts.
Are there any other questions I can answer? Perfect.